Time and again, powerful eruptions take place on the Sun. Coronal mass ejections spin billions of tons of hot solar plasma into space. And so-called flares release the power of more than 1 billion hydrogen bombs with their gamma-ray bursts.
It bubbles up and explodes. It is like fireworks, all the time and everywhere. And, of course, people find that fascinating. We want to understand where it comes from.
Because the solar outbursts are also dangerous. If these high-energy charged particles travel towards the Earth, our magnetic field protects us from the worst onslaught. But from time to time, particles enter the Earth's atmosphere by following the magnetic field lines. The best-case scenario is when they make air molecules glow, thereby creating the polar lights. The worst-case scenario is when they damage satellites, disrupt GPS and mobile telephone reception, and can even rock the power networks of entire countries. And so it is important to understand solar activity and even to be able to predict it in advance. These are the scientists who are keeping an eye on the Sun. Professor Sami Solanki and his team at the Max Planck Institute for Solar System Research in Katlenburg, Lindau are investigating the activity of the Sun.
For some years now, it has been clear that there is a major feature on the Sun which is really central for all these active phenomena. For the outbursts, the sunspots, the flares, the solar prominences and so on, and many other things. And that is the magnetic field.
A strong and complex magnetic field is caused by the rotation of the Sun and the movement of the bubbling gases. In many places, the magnetic field lines break through the surface in an apparently chaotic manner. Professor Solanki explains how solar flares arise using an everyday example: rubber bands.
When I pull the rubber band, it becomes progressively more difficult to continue to pull. The tension builds up. If I pull it apart, or attempt to make it into a funny shape, it twists and changes, and is pulled apart. And at some point, it becomes too much, and breaks away.
Something similar happens with the magnetic field lines on the Sun. They move with the bubbling gas. As they do so, their magnetic fields become twisted until suddenly vast amounts of energy are released in an outburst. In order to understand these processes on the Sun and predict the solar flares, the scientists must first find the smallest magnetic building blocks, the so-called flux tubes. However, they are comparatively small.
Each of these millions and millions of bundles of threads run through the Sun and end in general in one of these elemental building blocks of the magnetic field, in these flux tubes. And in order to untangle it all, I need to see these threads. I must be able to disentangle these flux tubes and see how they move, where they came from, and where they are going to.
What solar physicists need is an extremely powerful telescope. A telescope which, if it were used here on Earth, would be able to show a €1 coin in sharp focus from a distance of 200 kilometers. But even the biggest solar telescopes on Earth can only recognize structures as small as these with difficulty over a long period because of the turbulence in the Earth's atmosphere. There are space telescopes, it is true, but they can't be too large or too heavy, because every additional kilo of payload in the freight compartment of a rocket is extremely expensive. A brilliant idea! The solar physicists in Professor Solanki's team developed an enormous balloon telescope, its name Sunrise. The plan? They needed to build a large telescope with a mirror diameter of 1 meter, and then use helium to provide the necessary lift. Oh well, perhaps it would be better with one big balloon than lots of small ones. Then it could climb up to the edge of the atmosphere and observe the Sun, and there would be nothing else there to interfere with the picture. That at least was the idea, but would it actually work? Nobody had ever attempted to attach such a large telescope to a balloon before. The scientists had to work out lots of technical details in order to solve the new problems which cropped up in connection with this idea. For example, the problem of wind. If it is blowing hard, the pictures produced beneath the balloon, as it is buffeted about, will be out of focus. So the scientists had to find a way of stabilizing the picture produced by the telescope. The solution was a small movable mirror. It compensates actively all the time for the quivering of the beam of light emitted by the mirror of the telescope. After 6 years of construction, Sunrise was finally ready for launching.
When Sunrise was about to be launched, I was very nervous, and I think the entire team. There were lots of people working on it to make it possible. We were all very, very nervous, because launching a large balloon is always rather a tricky business.
In June 2009, the telescope Sunrise finally started out from its launching pad in Kiruna in northern Sweden. The helium balloon was intended to carry the telescope, which weighed about 2 tons to a height of 37 kilometers. That meant that Sunrise left 99% of the Earth's atmosphere behind it, which gave it a clear view of the Sun. For 5 days, the polar winds carried Sunrise round the North Pole. The telescope could observe the Sun day and night, because in summer the Sun never sets. And then it landed again, dramatically. Stormy winds blew the balloon off course above Canada. There was a risk that the telescope might come down over water. But finally, Sunrise crash-landed on Somerset Island, a remote Canadian island.
We were lucky. It came down on land. It was quite a violent landing, but the important things were not damaged. Above all, we were able to recover our data safely and take them home with us. They were packed in special containers and well protected, and that was when the fun started.
The fun consisted of all the information which the scientists in Professor Solanki's team had to evaluate. The data from the telescope showed the activity on the surface of the Sun in brilliant resolution, as it had never been seen before. And the search for the elementary building blocks of the magnetic field was successful too. For the first time, the scientists were able to trace and investigate the bright little dots on the Sun's surface, known as bright spots, over a longer period of time. These hot magnetic structures are the penetration points for the flux tubes which they had been looking for. Over the course of time, they become entangled and lead to outbursts.
Many years ago, we had indirect indications that they must exist, but until then, no one had ever seen them directly. And with Sunrise, we actually achieved it. That was a real breakthrough.
These tiny magnetic structures had been calculated in theory, but no one had ever seen them. Now the observations could flow into their theoretical models. The aim was to be able to predict the solar flares. But the scientists still lacked some important information, because the flight of the balloon telescope took place during one of the Sun's especially quiet phases, with very few sunspots or flares.
These small-scale magnetic structures were there, but we didn't manage to discover many of the things we wanted to learn about. We shall organize another flight. The Sun is very active again. This time, our aim will be to be able to predict, okay, now something is about to happen. Enough energy has accumulated and enough tension. Now we can start.
Sunrise will soon be flying again, and this time it will focus its attention on a solar outburst, or at least a sunspot. Perhaps that will be the next big step on the way to predicting solar storms.
Yeah.